Okay, and now that we've got a little bit of background on just what ax equal to b means, let's talk a little bit more about just what are matrix operations. In other words, once we have numbers, we have algebra. Once we have matrices, we also have some algebra that we can talk about there. There's a couple of ideas that are familiar, addition and multiplication. When I say multiplication, I mean that C here is a scalar, and that A is just like it was a moment ago. It could be matrices like the ones we've been seeing. Again, these don't have to be 3 by 3 matrices every time. It's just that it makes for nice examples. But you could imagine a 4 by 12 matrix or a 2 by 1 matrix, which is a vector, etc. So all of this still applies. But I can scale my matrix is what this means. I can multiply it by 3 and we'll do 2 and so forth. Okay? And these are the basic ideas. When I write something down like a plus b, we have to be careful about that. Because what if, for example, my matrices were of different sizes? How could I define addition over that? Well, it doesn't work out so well. But on the other hand, what I have in this case, it will work out because, as you can see, both of these are 3 by 3 matrices. So when I go to write something down like computing a plus b, well, that just makes sort of common sense, if you will. The idea is the top left entry, I add those together when I think about a plus b. The top middle entry, the top right entry. In other words, I just proceed by looking at the matching entries and doing the addition inside of the matrices. So, the first number, 3 plus negative 4. Right? The next number is going to be 1 plus 3 in this example. And then 0 plus negative 2. And I won't write the rest of these down in full detail like that, but I think you've got the idea. And likewise, I can go, well, all right, let's go a little faster, right? 4 plus 0 is 4. Negative 2 plus 0. 1 plus 1. And onward we go until we've computed all 9 entries of the addition that we're performing there. Okay, so that's how we would construct a plus b. And there is some notation worth mentioning that when I'm thinking about the ij entry, what does that mean, the ij entry? Well, the first of those is going to be a number. Maybe I is equal to 2, or I is equal to 3. That would be the second or the third row of my matrix. And I could think about the j as the column. Okay? So for example, I could write down a plus b 2, 3. What would that mean we're talking about? Well, that would mean we're talking about the second row and the third column. And so what we're going to get for the second row, third column entry is this 1 plus 1 entry, which is the 2 that we've got right here. Okay? So that's how that notation works. Might look a little cryptic at first, but it's usually somewhat helpful to look at things like this from time to time. What about scaling a matrix? The next thing to compute is 2a. Well, 2a, we can really do this one right in place, can't we? And let me save a little space by squashing this calculation. If I double all of these numbers, that's what it means to talk about 2a. So I'm going to have 6, 2, 2 times 0, it's 0. And likewise, just going onward, doubling each of these numbers in this case. And let's see if I can do this without forgetting how to do arithmetic. I think I've succeeded. Looks okay. Let's hope it does. We'll find out if I get any feedback. Now, what about this t? This is in the exponent of a matrix. You might think at first something like a squared or a cubed. We do have notation for that, and we have to first talk about what matrix products are. What is a matrix times another matrix? This is called the transpose, and it's not the same thing as a squared. In other words, that t isn't telling us to raise to a number power, a numerical exponent. It's telling us a set of instructions. So this notation looks kind of like a matrix squared, but it means something quite different. And what I do with the transpose is I'm going to take the first row of my matrix and write a new matrix where that's the first column. Another way of thinking about this is if we were to draw a diagonal line here, we're reflecting with mirror symmetry about that diagonal line, starting in the top left corner down to the bottom right. Okay, in other words, the 3 stays put by the mirror symmetry. The 1 reflects from the top middle entry to the middle entry of the let's say, the first column then. Okay? And then this 0 flips to that bottom left corner. Okay? Nothing on the diagonals changed, so we can copy those in a little faster here. And then really, if we've got that much of it down, it starts to complete itself fairly automatically. What I mean by that is, well, if the 0 moved to where the 7 was, the transpose says to move the 7 back up there to where the 0 was. And if we've got that, you can just follow the pattern. 3 and 7, what's between them? The 4. 3 and 7, what's between them is still the 4. Okay, and, well, we're almost done, so looks like the 1 has to move and the -3 has to swap with it. Okay, and so that's what we mean when we talk about the transpose of a matrix. Okay, so here's some basic operations. The only one that's left to talk about is a little bit more difficult, and that is, what about a matrix times a matrix?